Chemistry students, hey, Mr. Trimble here. Today we're going to do our first supplemental lesson reviewing the 3 types of chemical bonds. What you're going to want today is your chemistry notebook. We're going to be on the next available page in that notebook. Let's say you forgot to bring the notebook home from school. You can call the front office and they will go to my classroom or to your locker, pick it up, and they can bring it to you at the door. If you don't want to do that, find a notebook in your house and start with a brand new one. Maybe you want to go grab your English or social studies notebook and just flip to the back or find a new section in that. It really doesn't bother me. As long as you're taking notes, at the end of this, you are going to take a picture of your work and you're going to submit it to me through Google Classroom. If you really want, you can use any blank piece of paper. This is printer paper. It works great. Also, starting April 6th, if you go to the high school or any of the elementary schools or middle schools, from 9 a.m. to 11 a.m., they will have free pencils, paper, pencil sharpeners, pens, and crayons that you can pick up if you run out of paper while you're home. This is going to be a supplemental lesson. I am going to check that you did it. I want all of you to do this lesson with me. Although it does not affect your final grade in the Home Access Center gradebook, it is the first chance for you to get your brain rolling. It doesn't take long, and it's going to let me know that you have access to the internet and you know how to turn things in. All right, with that note, let's get started. Grab yourself a pencil, grab yourself a piece of paper. I'm going to use an iPad, and let's get started. The first thing I want you to do at the top of the page is give these notes a title. I'm going to write Chemical Bonds Review. I like to underline that. It's up to you what you do. If you are in your existing chemistry notebook we've been using all year, we're on page 15. If you're on a brand new one, it's fine. You don't have to have the same page number as me. That's just where I am, and I like to say it. We always start with an essential question. I want you to write essential question, so you know what this is. You know you can also write EQ if that makes you happy. All right, today I want you to be able to answer this one question, and that means you've succeeded. How do I identify and describe ionic, covalent, and metallic bonds? How do I identify and describe ionic, covalent, and metallic bonds? Remember that a chemical bond is just any time 2 or more atoms are stuck together via some chemical process. Let's draw a horizontal line. If you have lined paper, you already got that. I'm going to draw 3 columns here. I'm going to do my best to make these nice and clean, but you know, my handwriting can be pretty bad. Here we go, vertical, vertical, vertical. The first column is going to be called ionic. The second, let's write the word covalent. And then on the third one, let's write metallic. Beautiful. All right, I'm going to underline those just because that makes me happy. I'm going to first start with what are the key ways to identify these. Then we're going to get an example of each. I'm going to tell you their properties, and then you'll practice with 4 or 5 practice problems, and then write a summary at the end before you turn it in. Let's start with ionic bonds. I'm going to zoom in over here to make it nice and big. Ionic bonds occur between a metal and a nonmetal. Sometimes you'll have a polyatomic ion with that nonmetal, where it's multiple nonmetals put together in some more complex way. But for now, let's just think about it as a metal and a nonmetal. Covalent bonds, on the other hand, these are when we have a nonmetal bonded to a nonmetal. Now, you guys know you can have lots of nonmetals stuck together. Some of the organic compounds that make up your body are made of dozens or, many large numbers of nonmetals bonded together in these complex shapes. We're going to start with some pretty simple ones, but you always want nonmetals bonded together. Now, metallic bonds, easiest one of them all. This is just any time you have metals bonded to other metals. And metallic is interesting because it's often just a metal bonded to itself. A chunk of iron is metallically bonded, iron to iron. It's pretty straightforward. You can also do that with covalent bonds. Oxygen can bond to itself as O2. But of course, with ionic bonds, those always have to be two different types of atoms. One needs to be a metal, one needs to be a non-metal. All right, so here's where I've made it so far. You say, Mr. Trimble, I forgot, what is a metal? What is a non-metal? If you go to ptable.com, it's a website with a free periodic table. There's actually tons of these all over the internet. When you look at the periodic table, you see lots of different colors. This actually has, up here at the top, it has your metals and your nonmetals color-coded. And if you do that within the P-Table app, or if you already have your periodic table from class, then you probably already have this labeled. If you don't, let's draw ourselves a little line. Starts right above aluminum. All right? And if you're at home, you could mark this up on your iPad. You could do it really any way you want. Everything to the right side of that zigzag line, I like to call it the zigzag, let's just call those nonmetals. All right, we'll just lump them all together. There are some metalloids along the line. I don't even care about them right now. Just keep it simple. On the left side of that, anything over there, let's call them all metals. Now, some of those are alkali, some are alkaline earth, some of them are transition metals, and there's one little sneaky one in the top left, hydrogen, up here in the top left corner. It fits with all of its friends over here in the non-metal category. Hydrogen has a lot of its own little rules because it's such a small, simple little atom. I'm going to go back over here and let's keep moving. When I have an ionic bond, it's a metal and a non-metal, in this type of bond, electrons are transferred. Electrons are transferred. All right, and the electron jumps from one atom to another, which turns them into ions. So generally it is transferred, actually always, it is transferred from what we call the cation to the anion. The cation ends up with a positive charge because it loses electrons. Your anion ends up with a negative charge because it gains electrons. Remember, there's a corny joke. Cations are always positive because cats have paws. And I like to say that anions, it looks like the word onion. Onions make you cry. Crying is when you feel bad. That's kind of negative. That's the way I remember it. You remember it however you want. It doesn't bother me. All right, with a covalent bond, we know that electrons are shared. Now remember, these are valence electrons. The electrons on the outer ring of any given atom, these are shared, and they're generally shared in pairs. All right, it's always two of them. I give you one, you give me one, we share them together, and then we're both happy. Metallic bonds have something that in some ways is more simple and in other ways a little more complex. In a metal, when they all get together as friends, they have what we call delocalized electrons. Delocalized electrons. All right, delocalized electrons in a metallic bond, they are shared equally in a sea of electrons. A sea of electrons. All right, I'm going to zoom back out. If I'm moving too fast, you're welcome to pause the video. If I'm moving too slow, you are welcome to speed the video up with some of the settings that are down in the bottom of the YouTube video. All right, let's get an example of an ionic bond. The most common one, all right, I had this with breakfast this morning. It is a combination of a sodium metal and a chlorine nonmetal. Chlorine's a gas by itself, sodium's a metal by itself. If you look at the periodic table, I'm going to go back over here. Sodium is over here on the left side. It is in group 1. Group 1 tells us it has 1 valence electron. If I go over and look for chlorine, it's over here on the right side of the periodic table. It's up here in group 17. Group 17 always has 7 valence electrons. Really easy as long as you have a periodic table with you. So sodium gets 1 dot on the right side. Chlorine gets 7. I like to draw them one at a time going around in a circle. So chlorine gets 1, 2, 3, 4, 5, 6, and you know what? I'm going to break some rules. I'm going to draw the 7th one up there because I like to leave that lone electron on the left side. When sodium gets close to chlorine, because of the electronegativity and the ionization energy, that sodium is going to give or transfer its electron over to the chlorine. And when that happens, we're going to have a sodium 1 plus ion, that's the cation ion, and then we're going to have a chlorine 1 minus anion. At that point, these are 2 charged particles, and they start to act a little bit like magnets. There's an electrostatic force that makes these things stick together, a lot like the positive and negative side of a magnet when you stick those together. And we can put those together once they're bonded as NaCl. And that is sodium chloride. We always first write the name of the metal, and then we write the name of the nonmetal. But instead of writing chlorine, we change the N to De, chloride. All right, that was a big review of several days of class. That first one up there is called, I don't like orange, I want to make it brown, Lewis dot structure. Lewis dot. The second one, that was represented as ions. That third little picture is called a chemical formula. And then at the end, sodium chloride is the name of the ion. All right, I'm going to keep moving. Covalent bonds. Covalent bonds are pretty interesting. I'm going to move to purple. The most common covalently bonded molecule that you're going to run into, it's my favorite one, it's what my body is made of, mostly. It is made of hydrogen. Now remember, hydrogen is a non-metal, even though it's on the left side, and oxygen. So hydrogen and oxygen. Let's go back to the periodic table. Hydrogen is in the top left corner of the periodic table. Here it is. It has 1 valence electron. Oxygen is over here on the right side. It has 6 valence electrons. Let's draw it out. Hydrogen gets 1 dot. We generally start with that dot on the right side. Oxygen gets 1, 2, 3, 4, 5, 6. I like to go in a circle. All right, now this is a little bit different. Because they are both non-metals, the hydrogen will not transfer its electron to the oxygen. Instead, the hydrogen, no, I want green. The hydrogen is going to share these 2 electrons with one another. So oxygen can use hydrogens, and hydrogen can use oxygen's electron. The goal there is for both of these to have a stable octet. That means there's 8 valence electrons. That gives them the configuration of a noble gas. Now remember, hydrogen breaks all those rules because it can only have 2 electrons, because it's really, really small. So now hydrogen has a full outer shell. Oxygen, by sharing 1, has 7 valence electrons. Oxygen is going to need 1 more electron. So all it has to do, we're going to assume we're in this imaginary space with as much hydrogen as you could possibly have. I'm going to toss another hydrogen right up here, all right? And I'm going to put that hydrogen's valence electron on the bottom, just so I can draw it in this spot. And those 2 electrons will also be shared. Now I have 2 hydrogens, nice and stable, full outer shell. I have 1 oxygen, nice and stable, has a stable octet on the outside. And at this point, I can draw these as a bonded molecule of H. Here's H. Here's O. Here's another H. Instead of those two dots, now I'm going to draw just a straight line. That's called a single bond. It's one pair of electrons shared. And I'm going to make sure to draw these extra pairs on the other side of oxygen. That becomes really important as we move along. Don't forget to draw those 4 extra electrons. And then lastly, I'm going to draw it on the right side. No one writes this, right, when you're talking about H2O. We write that there are 2 hydrogens and 1 oxygen. So again, this is called the formula. The formula has subscripts, little numbers down low like a submarine. This over here, this represents the bonds. And then this guy up here, that is the Lewis dot diagram, or the Lewis dot structure. Last one. Metallic bonds. All right, I'm going to pick a metal that you use all the time. You have a wire containing this that charges your iPad. And I'm going to make this a little bit bigger because my picture's in the top right corner. We're going to use copper, just a bunch of copper stuck together. All right, so this diagram will look a little bit different. Copper generally has a 2+ charge. All right, that means there's 2 electrons that can end up floating around and being shared in this delocalized sea of electrons. So I'm going to start by drawing myself several copper atoms. Copper, copper, copper. And you know there are quadrillions of copper atoms that you're going to be dealing with. There's this unfathomable number. And now let's draw for each copper. I'm going to go ahead and say this guy has 2 electrons and they're just floating around. This guy over here has 2, they're floating around. Here's 2 floating around. And here's this guy that can have 2 floating around. And you can imagine this expanding in this giant lattice going outwards. And if you put that in a long ductile tube, then we call that a wire. So this particular electron, it can kind of move around, do its thing. This one can come up here and move around. They can be shared equally. And if we apply a charge to this, or a different charge to each side, we can make those electrons move. And that's what we call electricity, which is conducting through a metallic bond. I'm going to back it out. There are 2 key things I want you to know about each of these. Do you guys see this nice, simple little diagram you're making? This is a great little cheat sheet that you can use to study or even use on any open notes quiz. It's a great little thing that you can use. Hang on to this. All right, ionic bonds. Let's get 2 key properties. All right, the first, they will dissolve in water and they will conduct electricity only when they're dissolved in water. So I'm going to say ionic bonds conduct electricity when dissolved in water. When you dissolve an ionic bond in water, it will generally become what we call an electrolyte. There's a Y in there. Electrolytes are important. They're in a bunch of sports drinks like Gatorade. They're also in Pedialyte, which is a drink that you give to babies or young children whenever they get sick. That assists with your muscle function and your nervous system. And of course, your brain needs electrolytes to do its thinking. I'm going to go over here. Our covalent bonds. Now, covalent bonds are interesting. Some of these dissolve in water. Sugar dissolves in water. I hope so. That's what soda is made of. Dissolve in water. But silicon dioxide does not dissolve in water. That's what we make a glass out of. So it's interesting. When you drink a glass of water, the glass is covalently bonded. The water is covalently bonded. But any sugar that's in there, it's also a covalent bond which dissolves within the water. And if for some reason you put salt in your soda, then you'd have ionic bonds, those electrolytes, which would disassociate and float around. These will never conduct electricity. And, you know, there's probably some exception to that rule out there, but electricity. So in theory or in practice, perfectly distilled water will not conduct electricity, but it's really hard to find perfectly distilled water in your everyday life unless you go buy a bottle of it. Most water has dissolved ions. Last one, a metallic bond. These do not dissolve in water. And the easy way to think about that, if you go to the store and you buy an aluminum can with any kind of drink inside of it, that aluminum does not dissolve. Otherwise the can would dissolve and the soda would go everywhere. And so that's one easy way to think about it. Likewise, if boats, which are made of water, if they dissolved in water, then the boat would disappear and sink. So metal does not dissolve in water. And metal does conduct electricity. In fact, most things that we use that are related to electricity are made of metals. All right. Sort of the only one that might be kind of weird is silicone, which we end up using in semiconductors and computers, and those can end up being conductive or non-conductive depending on different properties that are applied to them. Don't worry about that for now, although that is what's happening inside your iPad. All right, I'm going to draw a horizontal line. You guys, that's the end of the notes, all right? Look at that. That was actually everything we did for the last month. Boom, all together in one little set of notes. Let's do a little practice work. All right, I'm actually just going to draw you some questions, and I'm going to have you work on these on your own. I'm going to start with name, formula. Just write this out with me, or fast forward until I've got it written. Type of bond. Will it dissolve? And lastly, will it conduct electricity? And you could write this even shorter if you want. You could say name, formula, bond, dissolve, conduct. It's whatever. It's your life. All right, on the left side, I am going to give you 5 different chemicals or 5 different substances. The first one is called potassium chloride. Please write these out with me. Potassium chloride, KCl. Make sure you notice that K is potassium and Cl is not carbon and iodine, it's chlorine. Very commonly mixed up. Silicon dioxide is number 2, also known as quartz or glass. And silicon dioxide is SiO with a subscript of 2. Our third one will be sugar. There's several different types of sugar. We're just going to use this one. It's C12H22O11. Our fourth one I want you to work on, aluminum. In England they call it aluminium. I think that's actually the correct pronunciation. It's just Al. Aluminum, one of the things we want to do with that, I like to write a +3 on there so that I know it's just aluminum by itself, and it's got 3 of those electrons that can be delocalized. And our last one on this list is calcium chloride. Calcium chloride. Ca, ooh, you guys, CaCl. Ooh, and you're like, CaCl, is that enough? If I go back over here to this particular guy, I can see calcium is in group 2. It has 2 valence electrons. Chlorine is in group 17, so it has 7. So we're going to need 2 chlorine atoms, CaCl2, in order to match the calcium charge so that everybody can become neutral. All right, what I want you to do, I'm not going to give you these answers. This is what you're going to do over the next few minutes. Take a look at this little sheet up top. It's got all the answers set out for you. Look at each one of these in your periodic table. Decide potassium and chlorine. Is that metal, metal, non-metal, non-metal, or metal, non-metal? Is it, what type of bond is it? Ionic, covalent, metallic. Just write that right here, whichever one you think it is. And then decide, will it dissolve? Yes, no, maybe. And will it conduct? Yes, no, only when dissolved. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's 15 words you have to write there. At the end of the week, I plan to post an answer key online, but I want you to do this yourself and submit it. Be bold. If you want to call your neighbor and talk about it, have a little video chat where you guys discuss this, that's totally fine with me. At the bottom, I want you to draw a horizontal line, all right? And actually here I am on the next page. I want you to write the word summary. Every set of notes should have a conclusion or a summary. What I want you to do at the end, when you're finished, write 2 to 5 complete sentences. All those sentences have to do is answer the essential question. I always like to make essential questions just a really good question that would be a good essay question on a test. How do I identify and describe ionic, covalent, and metallic bonds? Wouldn't that be a great test question? Or wouldn't that be a great thing to answer? Use these notes right here and write 2 to 5 sentences at the bottom. How do you identify and describe? You want to talk about metals, non-metals. I think it's good if you use the word cation and anion if it's relevant on there. And then when you describe them, are the electrons shared? Are the electrons transferred or stolen? Are they delocalized? Do they dissolve? Do they conduct electricity? You could write 1 sentence for each one of those. That'd be 3-sentence summary, and that would be awesome. When you finish with this, all right, you got a nice piece of paper, it's got these notes on it, you finished. First of all, hang on to it, keep it, you're gonna need this later. Take your iPad, go into the photo mode, all right, go vertical or horizontal, I don't actually care. Take a nice clean photo of this and then attach that photo to this Google Classroom post and make sure you press the button that says turn in. That will give me a chance to see your work, to read your summary. I'll give you like 5 points in Google Classroom just so you know that you did it. And then hang on to it. It's an important thing to hang on to. You guys, we are about to move forward next week. April 13th is next week. That's going to be the beginning of distance learning. That's going to be new material, which is going to be graded. As you know, we were 2 days away from taking a test on ionic, covalent, and metallic bonds. So we're going to jump back in. I'll give you guys some more practice on them. And then I'm not really sure how we're going to end up testing or quizzing on this, but I'll let you know next week when you jump back on. Please do this lesson. Please make sure you turn it in. It's going to let me know that you're awake and alive and your iPad works and your internet's working and that you're willing to jump in and learn some chemistry as we move forward. Thanks, guys. I'll see you next week. I am Groot.